We're going to find the starting conditions for our ordered triples that make our next terms equal to 0. So let's start with a sub 4. We'll substitute our formula for a sub n. Our starting a sub 3 cannot be equal to 0, so that means our second factor is equal to 0, and a1 equals a2. Let's call this condition number 1, and we'll keep track of it over here to the right. Let's check the next term, a5 equals 0, and we'll substitute. Here we have a2 equals a3, and we'll make this our second condition. And we'll go on to a6. a6 is 0, then this expression is going to be 0. This means a3 is going to be equal to a4. We'll substitute our expression for a4, so that's a3 times the absolute value of a2 minus a1. This is true when the second factor is equal to 1. And writing it algebraically, a2 is a1 plus or minus 1. We'll make this our third condition and add it to our list. And we'll go on to a7. When that's equal to 0, we have this expression is equal to 0 again, which gives us a5 equals a4. And substituting for a5, again, we have the second factor is equal to 1, which will give us our fourth condition. a3 is a2 plus or minus 1, and we'll add it to our list. And we'll continue with a8. When that's equal to 0, we'll substitute. This gives us a6 equals a5, and we'll substitute again. The second factor is equal to 1, and we'll substitute again for a4. Our starting ordered triples are all positive, so we can factor out a3 and pull it outside of the absolute value sign. We have two factors whose product is 1, so we have to have a3 is equal to 1, and then this second factor is equal to 1, which means inside the absolute value sign, we have a2 minus a1 must be equal to 2. And algebraically, this means a2 is a1 plus or minus 2. So both of these need to be satisfied, and we'll call this condition 5 and add it to our list and continue with a sub 9. And substituting, a6 equals a7, and substituting, this absolute value equals 1. So we'll substitute for a5, factor out the a4. We get a4 equals 1, and inside the absolute value, since this is always positive, we must have a3 minus a2 is equal to 2. Let's rewrite this first condition as a3 times the absolute value of a2 minus a1. We want this to be equal to 1, which means a3 equals 1, and our second factor is equal to 1. This condition looks familiar, and we see that we actually have this here in condition number 3. So we're going to have an a sub k that's equal to 0 before we get to a sub 9. We can also infer that for k greater than or equal to 10, by repeating this process, we're not going to find any new a sub k's that are equal to 0. So these are our 5 conditions. Now we need to count all the ordered triples that satisfy these. Let's list these out. These are the first 2. I'm going to break out this third one into 2 separate conditions. So that's a2 equals a1 plus 1 and a2 equals a1 minus 1. We'll count those separately. And same thing for this fourth condition. I'll break it out into a3 is a2 plus 1 and a3 is a2 minus 1. And then condition number 7 is going to be this last one. We're going to count each of these conditions separately, and then we're going to compare them pairwise to see when we have overlap, that is duplicate ordered triples that we're counting twice, and we'll subtract those. To make this easier, I'm going to show what these ordered triples actually will look like. So this first one is x, x, and y. The second one has the last 2 terms are the same. Here a2 is 1 more than x, and then y can be anything. If our first term is x, this one is x minus 1, and our third term can be anything. Our third term is 1 more than y, and here our third term is 1 less than y. For condition 7, our third term is 1, and then we have x and x plus 2, or x and x minus 2. Counting these without any regard to overlap, we have 100 ordered triples for condition 1, another 100 for condition 2. Here are our first 2 terms in the series must be consecutive integers between 1 and 10. There are 9 of them, and then y can be any of the 10, so that's a total of 90. Same thing here, 2 consecutive integers, and y can be any of the 10, and these 2 are also 90 ordered triples. Here we need 2 numbers that differ by 2, and this third term has to be 1, so this is just 8 ordered triples and another 8 ordered triples. Now we need to compare these pairwise so that we can see when our ordered triples have been double counted. So we'll start with condition 1, and and we'll compare it to condition 2. And we see that we're double counting all the triples where all three numbers are the same. And there are 10 of those. Comparing condition 1 to these other ones, we don't have any overlap between 1 and 3 because in 3, the first two terms have to differ by 1, but in 1, the first two terms must be the same. Same thing with 4, but with condition 5, if we have an ordered triple where the first two are the same and the third one is one more than the second, this one's going to be counted twice with condition 1 and condition 5. These are two consecutive integers between 1 and 10, and there are 9 of these. Comparing 1 and 6, triples that look like this, x, and x minus 1 are going to be counted in both of these, and there are another 9 of these. Comparing 1 and 7, for 1, our first two terms need to be the same, but that's not going to be true in condition 7, so there's no overlap here. Let's go on to condition 2. When we compare it to condition 3, if we have x plus 1, and then our third term is going to be the same as the second, so that's also x plus 1. That's another 9. Comparing 2 and 4, we have x minus 1, and another x minus 1, so another 9. For condition 2, the last two terms have to be the same, so 5 and 6 will give us the empty set. Let's compare 2 and 7. For this first subcase, if y is equal to 1, then we have x plus 2 is also equal to 1, which doesn't give us a valid x. But for our second subcase, when y is equal to 1, x minus 2 has to be 1 as well, which means x is equal to 3. So this gives us the ordered triple 3, 1, 1 that's going to be counted in both of these conditions, 2 and 7. So that's one more. Let's compare condition 3 to the others. There's no overlap with 4, but there is with 5. So we'll have x and x plus 1. And then by condition 5, our third term has to be one more than the second. So this is x plus 2. This is 3 consecutive integers between 1 and 10, and there are 8 of them. Let's compare 3 and 6. By condition 3, we have x and x plus 1. And by condition 6, our third term is going to be 1 less than the second, so we're back to x. 2 consecutive integers, there are 9 of them. Comparing 3 and 7. With 3, we have x and x plus 1, but with 7, we have x and either x plus 2 or x minus 2. So we're not going to have any overlap here. Let's go on to 4. When we compare 4 and 5, our first term is x and then x minus 1. And then by condition 5, our third term is 1 more than the second. So we're back to x. And there are 9 of these. Let's compare 4 and 6. The first two terms are x and x minus 1. And the third term is 1 less than that, so x minus 2. And there are 8 of these. Comparing 4 and 7. By 4, the middle term has to be 1 less than the first, but by 7, it has to be either 2 more or 2 less. So no overlap here. Let's compare 5. 5 and 6 won't have any overlap because the third terms are different. So we'll look for overlap with condition 7. Comparing to this first category, if we have y plus 1 over here is equal to 1, this gives us y equals 0, which is not one of the valid starting triplets. So this is the empty set. And we'll compare 6 and 7. By condition 6, the third term is y minus 1. By condition 7, that's equal to 1, which gives us y is equal to 2. And then again by condition 7, our first term has to be 2 more than that, or 4. So that's one ordered triple that gets counted twice. Now we're going to use pi to add all the triples in these first 7 conditions, and then we'll subtract all the triples that were counted twice this way. Adding these, we get 576. All the numbers down here total 82. So our answer is 494. If you'd like me to solve any more contest problems, please leave them in the comments.